The sky over Lyon went dark at 8:47 in the evening. Not cloudy, not dusk, dark. Streetlights flickered on by reflex, confused by a sun that had, seconds earlier, been blazing. Birds went silent. Somewhere in the crowd, a child started crying, and nobody laughed, because for a few seconds, adults who understood exactly what was happening felt the same primal jolt their ancestors felt for 100,000 years, every single time this occurred without explanation. A ring of fire hung where the sun used to be. And it was only the first of 3 things happening in the sky within a 24-hour window that will not repeat itself for years. This is the real story of the August 2026 sky event. The date was August 12, 2026. The location was northern Spain, one of the last European mainland countries to fall inside the path of totality for a total solar eclipse since 1999. For 27 years, Europeans wanting to stand inside the moon's shadow had to fly to the Arctic, or the Pacific, or the southern hemisphere. This time, the shadow came to them. NASA confirmed the eclipse's path months in advance, tracking it from northern Russia across Greenland and Iceland and down into a narrow corridor of northern Spain, with a small sliver of Portugal caught inside the line of totality. Outside that path, the eclipse widened into a partial event across nearly the entire northern hemisphere: Canada, the northern United States from Alaska to North Carolina, and most of mainland Europe. But the eclipse was never the whole story. It was the opening act. Before the sun had even risen that morning, 6 planets had already arranged themselves across the pre-dawn sky in a formation astronomers call a planetary alignment: Jupiter, Mercury, Mars, Uranus, Saturn, Neptune. 6 worlds, spanning hundreds of millions of miles of empty space, lined up along the same narrow band of sky as seen from Earth, visible in the hour before sunrise to anyone who knew where to look. 2 of them, Mars and Saturn, bright enough to catch with the naked eye; Uranus, faint enough to need binoculars; Neptune, distant enough to need a telescope. 6 planets, 1 eclipse, and something else was still coming. To put that morning in perspective, on an average pre-dawn morning, most casual skywatchers are lucky to spot 2 or 3 planets without help, and even that usually requires knowing exactly where and when to look. A 4-planet grouping tight enough to fit inside a single wide camera frame happens only a handful of times each decade. A 6-planet spread, spanning from the horizon to well overhead, sharing the same slice of sky in the same narrow hour before sunrise, is rare enough that most professional astronomers will only see it a few times across an entire career of nightly observation, and this was the 2nd time it had happened in 2026 alone. That night, after the sun and the moon had both gone down, the sky delivered its 3rd act. The Perseid meteor shower reached its peak. Not an ordinary peak, not a typical August night with a dozen meteors an hour, if you were lucky and patient. This one landed under a new moon, meaning 0 light pollution from the moon itself, producing what NASA and independent observatories alike called the finest meteor display of the year. Under fully dark skies, observers reported seeing between 80 and 100 meteors every single hour. 3 separate celestial phenomena, 1 24-hour window, 1 date on the calendar, a total solar eclipse, a 6-planet alignment, and the best meteor shower of 2026. Nobody expected all 3 to land on the same day. To understand why this mattered, you have to understand how rare each of these events already is on its own, and then understand what it means when a planet's orbital mechanics accidentally stack 3 of them together. Start with the eclipse. A total solar eclipse happens somewhere on Earth roughly every 18 months. That sounds almost routine, until you account for the fact that somewhere on Earth usually means open ocean, polar ice, or a strip of land so remote that fewer than a few thousand people will ever stand inside it. The moon's shadow during totality is only about 100 miles wide. Earth's surface is over 196 million square miles. The math is unforgiving. For any single point on the planet, a total solar eclipse passes overhead, on average, once every 375 years. Europe's mainland had waited 27 of those years already. Then add the alignment. 6 planets sharing the same visible arc of sky is not a matter of celestial coincidence dictated by some ancient clockwork. It is a rare intersection of 6 independent orbital periods: Mercury circling the Sun in 88 days, Neptune taking 165 years, all momentarily crossing into the same narrow slice of the observable sky from our exact vantage point on Earth. Astronomers had been tracking the build-up toward this exact configuration since a smaller 5-planet parade back in February of the same year. What happened in August was the bigger version, the rarer version. Then add the meteors. The Perseids happen every year, without fail, because Earth crosses the same debris trail every August as it orbits the Sun. Leftover ice and rock shed over centuries by a comet named 109P Swift-Tuttle, each fragment burning up in our atmosphere at over 130,000 miles per hour. The shower itself is reliable. What is not reliable is the moon. Most years, a bright moon washes out all but the brightest meteors, cutting visible rates by more than half. In 2026, the moon was new, gone, zero interference. For the first time in years, the Perseids were free to perform at full strength on the exact night skywatchers needed them to. 3 independent systems, lunar, solar, planetary, each operating on their own timeline for millions, sometimes billions of years. And on one 24-hour window in August 2026, all 3 lined up. Let's walk through it in order because the sequence matters. Before sunrise, the 6-planet alignment was already visible for anyone awake in the pre-dawn hours. Observers in New York reported their best viewing window falling between 5:18 and 5:34 in the morning. Jupiter hung low. Mercury, notoriously difficult to spot because of how close it stays to the sun's glare, was visible just above the horizon for a narrow band of time. Mars and Saturn, easier targets, sat higher and brighter. Uranus and Neptune required equipment, but for the patient observer with binoculars or a small telescope, all 6 planets were there, strung across the sky like beads on an invisible wire. Then came the day. As the sun rose higher, the eclipse began its slow crawl. For most of the northern hemisphere, this meant a partial eclipse, the moon taking a visible bite out of the sun's disk, the exact percentage of coverage depending entirely on location. In parts of the northern United States, from Alaska stretching down through North Carolina, skywatchers with certified eclipse glasses could watch the moon's silhouette creep across the sun's edge. But along one specific corridor, sweeping across northern Russia, through Greenland, over Iceland, and finally down into northern Spain and a small corner of Portugal, the moon did not just take a bite, it swallowed the sun whole. Totality. For those seconds, or in some locations up to a few minutes, the sky went dark in the middle of the day. Temperatures dropped, automatic streetlights triggered. And the sun's corona, its faint, ghostly outer atmosphere, invisible under normal daylight because the sun's surface brightness overwhelms it, became visible to the naked eye. A pale halo wrapped around a black circle where the sun had just been. That corona is the reason astronomers treat every total eclipse as more than a spectacle. It is one of the only windows scientists get to directly observe the sun's outer atmosphere from the ground without specialized equipment blocking out the sun's disk artificially. Solar physicists position instruments along the path of totality specifically to capture data during these brief windows, measuring the corona's temperature, its magnetic structure, the behavior of solar wind as it leaves the sun's atmosphere. Data that is difficult, in some cases nearly impossible, to gather any other way. Here's what most people don't know about the corona, and why scientists treat those few minutes of darkness as more valuable than entire months of ordinary solar observation. The sun's visible surface, the photosphere, sits at roughly 10,000 degrees Fahrenheit. That's hot enough to vaporize nearly every material known to exist on Earth. But the corona, the wispy outer atmosphere that only becomes visible during totality, runs far hotter, millions of degrees, an atmosphere thinner than the thinnest lab vacuum, somehow burning hundreds of times hotter than the dense, brilliant surface directly beneath it. Nobody has fully explained why. It's one of the oldest unsolved problems in solar physics, sitting quietly at the center of nearly every eclipse expedition for the better part of a century. Instruments on satellites can study the corona artificially, using a disk to block the sun's glare the same way the moon does naturally. But those artificial disks create a ring of scattered light around the edge, drowning out the faint, delicate structure closest to the sun's surface. Only a natural eclipse, with the moon's precise geometry blocking the photosphere completely while leaving the sky around it genuinely dark, lets ground-based instruments capture that inner region cleanly. That's what teams of solar physicists were doing in northern Spain on August 12th, while thousands of ordinary skywatchers stood beside them simply pointing cameras and phones at the sky, spectrometers, polarization filters, high-speed imaging equipment positioned along the narrow corridor of totality, all racing against a clock measured in minutes, sometimes seconds, to gather data that won't be collectible again from that location for decades. Every total eclipse is, in that sense, a closing window, a brief appointment the universe keeps with anyone patient enough or lucky enough to be standing in the right 100-mile-wide strip of Earth when it happens. Then, as the sun set and true darkness fell, the sky delivered its third act, the Perseids. Their radiant point, the spot in the sky the meteors appear to streak outward from, sits inside the constellation Perseus, which is how the shower earned its name. But the trick, seasoned skywatchers will tell you, is not to stare directly at the radiant. The best meteors, the long ones, the bright ones, the ones that leave a glowing trail lingering for a second or two after they've already vanished, tend to appear off to the sides. Predicted peak, 14:53 GMT on August 13th, meaning the overnight hours of August 12th into the 13th, offered the single best viewing window of the year. Under those new moon, zero-light pollution skies, observers in dark rural locations reported meteor counts climbing past 90 per hour. Some networks recorded rates approaching 100. Bright ones, colorful ones. Meteors leaving persistent trains, glowing ionized streaks that hang in the air for several seconds after the meteor itself has already burned out, a phenomenon caused by the extreme heat and speed of the particle's entry into the atmosphere. Meanwhile, the meteors themselves carried their own quiet piece of deep history. Every particle burning up overhead that night had broken off from Comet 109P Swift-Tuttle, a chunk of ice and rock roughly 16 miles across, discovered independently by two American astronomers in 1862. Swift-Tuttle takes about 133 years to complete one orbit around the Sun, swinging in from the outer solar system, shedding debris along the way, then retreating back out into the dark for over a century before its next close pass. The comet itself won't return anywhere near Earth again until the year 2126, but its debris trail doesn't need the comet present to keep producing meteors. Centuries of shed material remain scattered along its orbital path, a loose river of ice and dust drifting through space, and every August, without fail, Earth crosses directly through it. Each fragment, most no larger than a grain of sand, some the size of a pebble, slams into the upper atmosphere at over 130,000 miles per hour, vaporizing in a streak of superheated light that lasts less than a second. A single grain of sand, older than human civilization, ending its multi-million-mile journey in a flash of light over someone's backyard. 3 events, one day, millions of skywatchers across dozens of countries, looking up at the same sky for entirely different reasons within the same 24 hours. And that convergence raised a question that spread quickly through amateur astronomy forums and skywatching communities in the days leading up to the event, a question far bigger than how rare is this? Was it truly coincidence, or is there a deeper rhythm to Earth's position in the solar system that occasionally forces multiple independent systems into brief alignment? And if so, could that rhythm be predicted, mapped, and anticipated decades in advance, the same way eclipses themselves are calculated centuries ahead of time? Stay with me, because this is where the story gets more complicated than 3 items on a calendar. To really understand what August 12th meant, you have to go back further than 2026. You have to go back to the last time Europe's mainland stood inside the path of totality at all. That was August 1999. A generation of Europeans grew up hearing about it secondhand. The darkened skies over Cornwall, over parts of France, over Central Europe, the temperature drops, the sudden silence. For nearly 3 decades afterward, anyone on the European mainland who wanted to stand inside the moon's full shadow again had no choice but to travel. They flew to Svalbard in 2015, chasing a brief Arctic totality. They crossed the Atlantic in 2017 and again in 2024 for the eclipses that swept across North America. They chased partial glimpses in between, craning their necks at 80 and 90% coverage, never quite getting the full experience. 27 years is a long wait for a natural event that, somewhere on Earth, happens roughly every 18 months. It is a reminder of just how selective this planet is about who gets to witness totality directly, and how much of it depends on nothing more than the geometry of a 100-mile-wide shadow crossing a planet covered mostly in ocean. So when NASA's eclipse calculators confirmed, years in advance, that the shadow's path in August 2026 would finally sweep back across the European mainland, through northern Spain, catching a sliver of Portugal along the edge, skywatching communities across the continent began planning for it the way people plan around solar milestones only a handful of times per century. But even that framing undersells what actually happened, because the eclipse was never going to stand alone. Rewind 6 months, to February 2026. That month, skywatchers were treated to a preview, a 5 and then 6-planet parade, timed alongside an annular Ring of Fire solar eclipse on February 17th. It was, at the time, described by observers as one of the most concentrated stretches of celestial activity in years. Multiple planets visible together, tidal effects worth noting, a solar eclipse of its own. For a few weeks, it looked like February would be remembered as 2026's standout month for skywatching. Then August happened, and February quietly became the warm-up act, because whatever alignment mechanics produced February's parade were still in motion 6 months later, when Jupiter, Mercury, Mars, Uranus, Saturn, and Neptune drifted back into a shared band of pre-dawn sky, this time not alongside an annular eclipse, but a total one, and not alongside an ordinary meteor shower, but the best one of the year. That's the pattern worth sitting with for a second. 2 planetary parades, 2 solar eclipses, 1 meteor shower peaking at maximum strength, all compressed into a single calendar year, with August 12th sitting at the center of it, holding 3 of those events inside one 24-hour window. Nobody plans a year like that. It simply happens, when enough independent orbital clocks tick past the same point at close to the same time. That question is where the more provocative voices in the skywatching world start to speculate. Some independent researchers who track long-term planetary cycles have pointed to the earlier 5-planet parade in February of the same year as evidence of something bigger, a broader planetary alignment period stretching across 2026, with the August convergence representing its most extreme expression. Under this framing, 2026 was never just a year with a few good sky events scattered randomly across the calendar. It was, in their view, a rare planetary alignment season, one where Earth's orbital position and the outer planets' slower orbits happened to sync up across multiple months, producing not one standout night, but a cluster of them. It's a compelling idea. Orbital mechanics are, after all, deterministic. Every planet's position on any future date can be calculated with extraordinary precision. If February's parade and August's convergence share a common underlying cycle, the argument goes, that cycle should be traceable and predictable decades out. Mainstream astronomers are more careful with that framing. The reality, most professional astronomers will tell you, is less mysterious and more mathematical. Planetary alignments of 5, 6, even 7 planets are not evidence of some hidden synchronized cycle. They are the expected calculable byproduct of planets with wildly different orbital periods occasionally drifting into the same visible slice of sky, the same way 6 people walking at different speeds around a track will occasionally end up bunched together at the same point purely by the math of their different paces. It happens. It's rare enough to be exciting. But it is not evidence of a deeper hidden rhythm. It is simply what you'd expect if you ran the numbers far enough forward or backward in time. As for the eclipse landing on the exact same day as the meteor showers peak, astronomers are equally direct. That part is genuine coincidence, in the purest mathematical sense. The moon's orbital cycle, which governs eclipses, and Earth's yearly crossing through the Swift-Tuttle debris trail, which governs the Perseids, operate on completely independent timelines. There is no shared mechanism linking them. Most years they miss each other by weeks or months. This year, by chance, they landed within hours. Rare, real, but not mysterious in the way some corners of the internet wanted it to be. Still, mainstream caution doesn't erase the numbers. It just reframes them. And the numbers, once you actually stack them side by side, are strange enough on their own without needing a hidden mechanism behind them. Anomaly 1. The eclipse itself was a geographic outlier. Most total solar eclipses trace paths across ocean, ice, or sparsely populated terrain because Earth's surface is overwhelmingly water. A path crossing directly through a heavily populated stretch of mainland Europe, after a 27-year absence, put totality within a few hours' drive of tens of millions of people who, in any other year, would have needed a passport, a flight, and a great deal of luck to see the same thing. Anomaly 2. The meteor showers timing against the lunar cycle. The Perseids peak on essentially the same August date every single year, give or take 24 hours, because Earth's crossing through the Swift-Tuttle debris trail is locked to the calendar. But the moon's phase on that date shifts every year, because the lunar cycle and the solar year don't divide evenly. Most years, the Perseids peak somewhere in the middle of the moon's 29.5-day cycle, a half-lit or gibbous moon, bright enough to wash out 30, sometimes 50% of the fainter meteors. A new moon landing exactly on peak night is not something that happens on request. It happens on its own schedule, and 2026 was one of those years the schedule cooperated. Anomaly 3. The planetary alignment wasn't a 2 or 3 planet grouping, the kind that happens multiple times most years and barely makes headlines. 6 planets sharing a visible arc of sky, 4 of them close enough together to be framed in a single wide-angle photograph before sunrise, is a configuration that requires the slower-moving outer planets, Uranus with its 84-year orbit, Neptune with its 165-year orbit, to be sitting in roughly the right section of the sky at the same time the faster inner planets swing past. Mercury alone completes an orbit in under 3 months, meaning its position on any given day is essentially a coin flip relative to the outer planet's near-frozen pace. For all 6 to land in the same visible band at the same pre-dawn hour on the same morning as a total solar eclipse required years of independent orbital motion to happen to intersect at exactly the right moment. 3 separate anomalies, 3 separate causes, and all 3 converging on one 24-hour stretch of one specific year. And maybe that's the more interesting story anyway, because here's the part that tends to get lost in the specifics of dates and degrees and meteor counts. None of this had to line up. The moon didn't have to be new on the exact night the Perseids peaked. The 6 planets didn't have to drift into visual alignment in the exact same month as a total solar eclipse crossing a landmass most of them hadn't seen totality on in nearly 3 decades. Every one of these systems has been running on its own separate clock for longer than human civilization has existed. The moon's 29.5-day cycle, the planet's individual orbits ranging from months to centuries, comet debris scattered across millions of years of solar system history. And for one 24-hour window, purely by the mechanics of orbital motion, they happen to overlap. That overlap is the part worth sitting with, because it puts a number on something most people never think about, how insignificant a single human lifetime actually is, measured against the clockwork of the solar system. The six-planet alignment that gathered before sunrise on August 12th won't reassemble in that exact configuration for years. The next total solar eclipse to cross mainland Europe again isn't scheduled for decades. And the Perseids, reliable as they are every August, won't line up with a new moon and a total eclipse on the same calendar date again for a very long time.